All right, so yeah, I'm recording now. So yes, I think this is relatively straightforward. Now, theta measured in radians is equal to x over r. That's where the whole circumference equation comes from, right? When we say c is equal to 2 pi r, the reason for that is there are 2 pi radians in a full circle, and the arc length that we're talking about is c. So 2 pi radians for a full circle. That arc length is the entire length of the circle. So theta is equal to x over r. And actually, specifically, this is an incorrectness. I should say by definition. X being the length of the entire circle. In this case, 2 pi being the amount of radians in a full circle. And so yes, c is equal to 2 pi r, or this you can solve for the entire circumference to be 20 pi feet. From there, I definitely think that iteration of division is your best bet. If we're talking about half of the circle, we're talking about half the circumference, a quarter of the circle, a sixth of the circle, eighth of the circle, and 12th of a circle. And so with that being said, I think that is like the straightforward response to it. Of course, if there are any questions, please don't hesitate to ask. But right, Rachel asks here, converting pi into 3.14 and multiplying everything together, would that be okay for the exam? What a great question. Now, I am going to say this. I am not necessarily sure. I know that in the past we've wanted things in terms of pi. Let me look very quickly at the specific wording of this review packet specifically, because it will say it specifically. Now, it says you are encouraged. It's not definite, right? It says you are encouraged to write pi instead of 3.14, 2 pi instead of 6.28. So no, I do not think multiplying by 3.14 is wrong. You're fine. Now, of course, if that does change, I will make sure that Yaverbal makes sure that the exam will state so, and it will be very, very clear that we want to keep it in terms of pi. But by that same token, if you are comfortable with converting pi into 3.14, there's no difference than with just leaving it, right? So instead of doing 20 times 3.14, you just leave it as pi. But very, very good question. Like I said, in the past, we have made it a necessity, but then the review sheet also states it. So I think that we're probably gonna leave it the way it is, where you can either leave it in pi or convert. But I totally implore you, all my answers you'll see are going to be in terms of pi. And so with that being said, you are definitely encouraged to leave it in terms of pi. Now, as far as the other question as part of deconstruct one, it's the same thing just with one. So if you understood this, you understand that. So I don't think it's necessarily imperative to go over. Would it be okay to answer in fractions instead of 5 pi over 3? We can write 1.66 pi. Yeah, Gabrielle, that's the exact same thing. I think that is 100% okay. As far as I'm concerned, I don't think we're requiring you to leave things in fractions. Like I said, if that changes, I will make sure that it is implicit, both in the instructions of the exam and in any sort of, like when we post the assignment, I'll make sure the assignment says so. But I don't think we are going to push for you to leave it in fractions and leave it in terms of pi, right? As far as I'm concerned, I think that converting fractions to decimals is totally cool. Because you'll see I'll even do it in some cases anyway. You're very, very welcome, Gabriel. Any other questions about this one? No, because you guys are asking good questions. But I think you guys got this, which is good. Like, and that's what I like to. Let's see. Cool. All right. Cool. All right. So let me stop. I'm gonna first stop recording because now I'm done with this. Pause. As I said, this all has to do with the unit circle, where each part of the right triangle represents either cosine and sine. The x, I'm doing this for the recording, sorry everybody. The x represents a cosine and the y represents the sine. When we were talking about simple harmonic oscillation, right, the function that describes simple harmonic oscillation is that of a cosine function, in which we have an oscillator that goes from a maximum to a minimum back to a maximum. Cosine is a part of a whole. Cosine is a description of a part of the cycle. As we can see, when we start out, right, if we look at our very first set, and I'm going to always do cosine as the red. When we start out, at the very beginning, the cosine, the x value, is the same thing as the radius, right? This, remember, all of these lines represent radius, and all of these are technically a radius of 1, right? That's why it's a unit circle, 1 unit. And so when we look at 0, right, when there's no angle, when there is no part of a cycle, we start out at the maximum. But as we go forward, as the cycle continues, you'll see that the cosine part gets smaller and smaller and smaller until when we reach to the 90 degree, in other words, 1/4 of a cycle, right? 1/4 of a cycle. What is cosine? Cosine is 0. There is no x, right? There is no x anymore. We're now at the equilibrium. But then the cosine starts to increase. We go to here, and then here, and then here, and then finally we're at negative amplitude, right? So we go from amplitude to negative amplitude at every single part of the cycle, right? We're changing our position, right? Because it's a cosine function. So the question is, though, where do we get these values? How do we know radical 2 over 2? How do we know radical 2 over 3? How do we know 1/2? Where do all of those values come from? And those are the diagrams that are in question, right? And that's totally the trig aspect of it. So first and foremost, I'll just stop right here. Any questions about the unit circle in general, right? The unit circle is all about a bunch of triangles that show us what part of that angle, what part of the triangle is sine and cosine. Right. Okay, good. Yeah, as long as you're right there. And I'll show you how we get that, right? But we're okay? Okay, so far? Yeah. All right. So let me show you what these diagrams are. So here's the first diagram. All right. So right here, pi over 4, that's a 45-degree angle. Okay, 45-degree angle. Now, there's something about a 45-degree angle right triangle, and that is that it's an isosceles right triangle. So we know traditionally in Pythagorean's theorem, a squared plus b squared is equal to c squared, right? However, in an isosceles right triangle, a and b are equal to each other. Well, good, Bobby, that's fine. Oh, it's the one thing that you understood past tense and you wish you remembered it. Well, hopefully this jogged your memory, right? Because these are the special right triangles, right? In an isosceles right triangle. And what does isosceles mean? Same base angle, same sides, right? They have the same length of sides and they have the same length of the base angle. So isosceles right triangle is a right triangle in which the two legs of the triangle, and I color-coded it here, orange and green, are the same. And so if b is equal to a, I can substitute it in, right? I could throw that sucker into the equation. And so I have a squared plus a squared is equal to 1 squared. Now, why is this 1? Unit circle. The radius, the hypotenuse, will always be 1. Okay, 2a squared is equal to 1. A is equal to the square root of 1/2. And so simplified, I get a is equal to the square root of 2 over 2, which is also equal to b. So what is the cosine of pi over 4? Well, the cosine of pi over 4 is the x value. Now, in this case, it's the same as the sine, but here it is, the x value, the one that's horizontal, radical 2 over 2. So yes, of course, you could throw it into a calculator, but the diagram showing it is right here. This is the diagram. Hey, that's the sketch. Any questions? Are we okay? Of course, this is being recorded. You can review this. Okay. 1 second. Okay. Good talk. All right. Sorry. talking to the boss man, getting some information. And I got it, but I won't share it with you. Not till it's pertinent. But no, any questions? Sorry about that. I am, why am I phasing? I don't like that. I hate that green screen flicker. But no questions? We're okay? Once again, isosceles right triangle, meaning that the sides are equal, and that allows us to make this substitution. We're able to say a squared plus a squared instead of a squared plus b squared, because a is equal to b. And like I said, c is equal to 1, which is the same for all of these. But yeah? All right. The second one, all right? So pi over 6, which is 30 degrees, and pi over 3, which is 60 degrees, are the same triangle, right? A 30, 60, 90. So pi over 6 is 30 degrees. Pi over 3 is 60 degrees. It's so annoying, 6 and 3 like that. But that's right. It's fractions of 180, right? So that's 30. So this makes a 30, 60, 90 triangle. And so we can, the diagram, right? So these are the diagrams here. But if you wanted a reason why, we start with an equilateral triangle. All right, an equilateral triangle being equal on all sides, 1, 1, and 1. From there, what we're able to do is draw an altitude, right? What's an altitude? It's simply a line that's at right angle to the base, right? It's like the height of the triangle. And what that ends up doing is cutting that side in half. Okay, so we already know that the base of the triangle, the cosine, right, of, right, so this is the cosine of pi over 3, okay? Once again, that's 60 degrees. The cosine of pi over 3 is 1/2. So we're actually already done right here. Right, there it is. Cosine of pi over 3 we already have is 1/2. Cosine being the x to it. But the question is, what is the y? What is the sine? Right? And so we have to solve for it. So we do a squared plus b squared is equal to c squared. What do we get? A squared plus b squared is c squared. A squared plus 1/2 squared, because we know that the base is 1/2, is equal to 1 squared, because we know the radius of the unit circle, the hypotenuse of that triangle is always 1, right? It's just what we keep on doing so that we have the unit circle aspect of it. And then we simplify. A squared plus 1/4 is equal to 1, squaring both of these to get that. Subtract 1/4, we get 3/4, square root it, and we're left with this. A is equal to the square root of 3 over 2. And so what that means is the sine of pi over 3 is equal to the square root of 3 over 2. And that is that relationship, right? A 30, 60, 90 triangle has x, 1/2 x, and rad 3 over 2x. Hopefully, Skylar, this is now coming back to you in full force. So these are the diagrams here. Like, this is just the explanation stuff that I wrote on the side, but the actual diagrams for credit, this is it right here. Right? To find the cosine of pi over 4, we draw an isosceles right triangle with pi over 2, rad 2 over 2 and rad 2 over 2. Boom, this is the cosine because it's the x value. For the sine of pi over 6, opposite the pi over 6, right, the vertical aspect, right, the y is going to be 1/2. And how do I know that? If I come back here to this diagram here, you can see opposite the pi over 6, right? These share the same triangle, but it's all about orientation and how you're looking at it. Opposite the pi over 6, the vertical aspect in this case, right, because of the way the triangle is situated, is 1/2. This right here is the sine of pi over 6. Remember, sine is the y axis, the up, down. The cosine of pi over 3, well, like I said, we just did it. Here's pi over 3. The cosine represents the x-axis. And so when I make my little triangle, I have 1/2 here on the x-axis. Yeah? Good so far? No questions? This last one's a little bit of a trick, because 5 pi over 6 is not one of those special right triangles, but it turns out that all of these incremental triangles, all these incremental angles, can be turned into those triangles. All right, well, good, Quasi? All right. Well, if Quasi's fine, then we all must be fine. But no, we're all right? All right. This one here, however, 5 pi over 6, well, what angle is that, right? Okay, good. Right, exactly, exactly. And that's the trick, right? That's, yeah, it's all about reference angle. So 5 pi over 6, how am I supposed to figure that out? What triangle does that make? Well, 5 pi over 6 is an angle that sweeps this way, as you can see. And so if the whole thing, right, is pi, right, one straight line is 180 degrees, so pi is equal to 180 degrees, right? If that whole thing is pi, then what is this angle that's left over? Oh, this angle that left over is pi over 6. In other words, pi minus 5 pi over 6 is pi over 6. And so, oh, look at that, pi over 6, I've got that angle again, which means that I know that opposite the pi over 6 is 1/2, right? Once again, looking back at this triangle here, opposite pi over 6 is 1/2, and next to pi over 6 is radical 3 over 2. Sorry, my thing's a little bit delayed. Let's see. Yep, it's back again, right? And so here's the triangle here. You can see it's set up this way where opposite is 1/2 and next to it is, in this case, right, and this is the trick, negative rad 3 over 2. Why negative? Because in the x now, we're in the negative direction, right? We're not in the positive direction like we were before. We're in the negative direction, so negative rad 3 over 2. But in this case, it doesn't actually matter. As you can see, we're doing the sine, which is the y-axis. No, fair enough, Quaz. I was just joking. That's why I'm asking. Any questions about this? Are we all right? Okay. Because we're about to get into the true meat and potatoes. What I believe is going to be the brunt of the exam. I'm not promising anything, right? Because this is the skeleton of the exam. The actual exam is obviously going to look like this, but it won't necessarily be exactly like this. But I think the meat and potatoes of the exam is the next two sections, in my opinion. Okay. All right. So pause. There we go. Now I'm resuming the recording because I did it right this time. But now I announced it, so that means I did it wrong before. And share screen. Okay. So for the first question, just a heads up, is my screen still sharing with you guys, or is there like a big black thing covering it? You guys can see my screen just fine? Good. Okay, yeah. All right, so on a windy day, an old but tiny barn door, why does that have to be tiny, swings back and forth in a steady pattern. Why do you read that? Oh, it doesn't matter. It oscillates each time the door swings fully out, then fully back in. What the hell is going on? Why are you doing that? It's bothering me a lot. I'm so sorry. Thank you. Each time the door swings fully out, then fully back in, the round trip is considered a cycle. All right, so we have something that's traveling cyclical, right? Given this rate of oscillation for this barn door is described by an angular frequency of omega being 628 radians per second. How many full cycles per hour, and I didn't do the per hour part, but we'll do the per hour part in a second. How many full cycles per hour is done by this barn door? Okay, well, the omega is 628 radians per second, right? We want to know how many cycles per hour. However, I'm solving for cycles per second. How many radians is one cycle? I'm asking you guys. How many radians is one cycle? Yes, Kat, you're absolutely right. There are 2 pi radians in a cycle. There is approximately 6.28 radians per cycle. And so to turn my angular frequency of radians per second into cycles per second, what I did is multiply it by 1 cycle every 2 pi radians. In other words, radians go by, and what I'm left with is 300, and this is very clever of Yerbom to do, 314 cycles per second Sorry, 314 over pi cycles per second, right? That's what I end up getting, right? So the 628 divided by 2, I get 314 over pi. And so what is that? That's approximately 100 cycles per second, because pi is approximately 3.14, right? So I do that division and I get approximately 100 cycles per second. All right. So are we following me there? Are we okay with that? With that reasoning? Did anybody get that as an answer? Now, this isn't cycles per hour. I'll do the cycles per hour in just a moment. It's just one more conversion. But are we okay so far? Honestly, right, and I believe you did, and that's kind of that's why I like this question so much. Is it's deceptively simple. It's deceptively simple. But Kat, does that make sense? Does this as a concept make sense? If we know how much if we know how much radians per second, and we know that a cycle is 2 pi radians, all we have to do is do that conversion, right? That's all we have to do is just go from radians per second to cycles per second by utilizing 2 pi radians. And by the same token, if it asked how many half cycles does it do per second, then I just turn this into pi, right? I say half cycle pi, right? And I can do the exact same thing. Yes. Good. No, but perfect. Yes, that's the trick. That's the trick for this question. So I'm happy I'm happy this question gave you trouble, because it's a very easy one to go, no, look, it's actually not that hard. Don't worry about it. Like, don't freak out. But now the last part is like turning this into cycles per hour, because the Everbomb wants to suffer us. Got it. Yes. Be careful. Make sure that you have this canceling out. Like, did I erase anything? Yeah. Make sure you have this canceling out like I did there. Yeah. Because if you do it the wrong way, then obviously you multiply instead of divide. So now 100 cycles per second. Let's convert that to hour, right? I know. So I'm going to write it here. That's 100 cycles per second, right? And I know that there are 60 seconds in 1 minute. And I know that there are 60 minutes in 1 hour. And so you can see same exact dimensional analysis crossing out, right? Seconds, minutes. I'm going to have cycles per hour. And so 100 times 3,600. Is that right? I think I did that right. Confirm for me, everybody, that I multiplied that right. That should be 3,600 times 100, which is going to be 3,600,000. Let's see if that's right. 3,600,000. That's the 2 zeros from before. No, it should be. There we go. That's what it is. 360,000 cycles per hour. That should be correct. Hopefully. Check my math, everybody. Check my math. 60. No, I'll check my own math. I don't need you people. What do I mean by you people? You students. Students are people. 100 times 60 times 60. Yeah, I did it right. Good. All right, so same exact thing, it's just a conversion. All right, so we're all right? We're good so far? Any questions? Like I said, I think this is the densest part of all this. So stop me if I'm very possible that you might have. Which, if you did, then kudos to you. I'm happy. No, sorry, Scott. Yes, fair enough. Now the next question says, measured in megahertz, which is not a convenient thing to do here. I mean, it's not too bad. What is the standard frequency of the barn? Okay. Well, what is standard frequency? Standard frequency is, let me say that again, cycles per second, right? That is what a standard frequency is. It's how much cycles you do per second. So we already solved for it, right? And the reason why you're asked to do a conversion is simply because the answer is already there. You're just asked to now turn it into kilohertz. In other words, like just like change it up a little bit. But you already technically solved for it. 100 cycles per second is the standard frequency, because that's what standard frequency is, cycles per second. While period is the inverse of that, seconds per cycle, right? And we'll get to that in just a moment. So the standard frequency is 100 hertz, right? Which, by the way, what is a hertz? 1 over seconds. That's all it is. It literally is an inverse second, which is what we have here, cycles per second, inverse second. So 100 hertz, which is, right, so it's approximately 100 hertz. So it's approximately 0.1 kilohertz, right? Divide by 1,000. So we get 0.1, right? So that was another one that's just very straightforward. There really isn't anything too crazy there. But are we okay with that? Right? Remember that standard frequency is cycles per second. Period, however, is seconds per cycle. And so all we have to do is inverse our frequency to get our period. And so we get 1 over 100 seconds, which is, right, 0.01 second, right? So there will be an oscillation every hundredth of a second, right? So every hundredth of a second, we see an oscillation. So that barn door is going crazy. Any questions? All right. Yeah. All right. A heavy mass, the next question. A heavy mass is attached to the end of a long, tight horizontal spring. The mass is held at rest at x is equal to 3 centimeters from the spring's equilibrium position. The other end of the spring is fixed to a wall. I don't know why I'm scrolling that as well. The other end of the spring is fixed to a wall. The spring has a stiffness of 4,000 newtons per meter, and the mass attached is 5 kilograms. And to repeat, when the initial velocity is 0 meters per second, x is equal to 3 centimeters, which means that's what it's pulled to. It's maximum displacement from the equilibrium. So the first question says, find the value of omega. Now, from lab and lecture, we determined that the omega of a spring is radical k over m. Now, in lecture and in lab, how did we do that? Well, we saw that T for a spring is equal to 2 pi radical m over k. And we also know that period by definition is 2 pi over omega, right? Therefore, the omega of a spring must be equal to the radical k over m, right? We have m over k here, but it's the inverse. Therefore, the omega must be k over m. In lecture, we used Newton's laws to determine what the acceleration of the object was. And then we did a little bit of calculus to determine the original equation, right? Right here. This original equation here, y is equal to a cosine omega t, right? So in two different ways, we were able to determine the same thing, where this omega, right, for a spring is the radical k over m. And so with that being said, if we're asked to solve for the omega of the spring, we are simply plugging and chugging. If omega of a spring is radical k over m, then that means that the omega of this spring is 4,000 newtons per meter divided by 5 kilograms. Therefore, the omega of the spring is 28.3 radians per second. So I'm going to stop right there. Are there any questions? Right? Woof. If we know the k value and we know the mass on the spring, then we know the omega. Same thing for a pendulum. The omega for a pendulum is equal to the square root of g over L. All right? These are known to us, right? We saw this as well. Once again, the period for a pendulum was 2 pi radical L over G. So the same exact logic, this right here must be equal to 1 over omega, the inverse of omega, just flipping it upside down. But I can promise you this much. It is that straightforward. The omega of a spring is k over m. The omega of a pendulum is g over L. And so if you know g and you know L, you know the omega of a pendulum. If you know k and you know m, you know the omega of a spring. We're all right? Okay. Now, as far as amplitude is concerned, that's the easiest. Amplitude is the maximum displacement from the equilibrium. So when we take the spring and we stretch it to a certain point and let go, where we stretched it to is the amplitude. And so in this case, the amplitude, if I'm not mistaken, I did change this. Yeah, the amplitude is 3 centimeters. Nice and simple, right? The amplitude is the maximum displacement from the equilibrium. Therefore, right, the amplitude in this case is 3 centimeters. What's the period? Well, as I said before, period is 2 pi over omega, but we also know the period of a spring in another way, right? This is from lab 2. Period of a spring is 2 pi radical uh, m over k, right? So either by using this equation, which you kind of did already right here, right? Either using this equation, you can solve for the period, or now that we know the omega, we can throw it into this definition. T is by definition 2 pi over omega. Oh, that's a shame. All right, thank you, Kellyanna. I greatly appreciate it. Yeah, that sucks. Well, she could always watch the recording, right? Like that's why we do the recording, so that's fine. That sucks. But yeah, there's the recording, so she'll be able to get from that. And so I'm talking to you. Right, who was it? It was Veronica, right? Yeah. So Veronica, I'm talking to you right now. If you're watching the recording and you have any questions, don't hesitate to email me. Now I'm talking to the rest of the class. That is Veronica. If you have any questions, don't hesitate to email me, or message me here in the chat, or speak, anything like that. But we're okay as far as solving the period. In the end, you're going to get 0.71 pi seconds. Now I left it in terms of pi. If you wanted to turn it into, a number that isn't pi, then multiply that by 3.14, and then you've got a number without pi in it, right? But I left it in terms of pi because on this exam, we implore you to do it. But I don't think that it's going to be a requirement because it wasn't a requirement for the review. But of course, like I said, you'll be informed. I promise you that. But no questions. We're okay here. Once again, T is equal to 2 pi over omega. We just solved for the omega, 28.3 radians per second, and therefore we can solve then for the period. All right. Now the next set of questions, right, asks us to determine the position of the mass at all of these different times, right? 1 second, 5 second, but I only wanted you to do 0, 1, and 5, not the other ones. So 0, 1, and 5, just 1, 2, and 3. Right? That is what I said. Hopefully I said that. Please let me say it. Did I say that? Yeah, 4 through 7, right? So just 1, 2, and 3. How are we going to do that? Well, we know the equation that describes the position of a simple harmonic oscillator in respect to time, y is equal to a cosine omega t. That is an equation that we learned is the model of motion for a simple harmonic oscillator. And thankfully, based on the question, we now know the amplitude, which is 3 centimeters, and the omega, which, right, that's correct, 28.3. Yes, good. I just want to make sure I change it, right? We know the omega is 28.3 radians. And so now all we have to do for these times is plug in for t, right? And so for question 1, we're going to have y is equal to 3 centimeters multiplied by the cosine of 28.3 radians per second times the time. So the first one is t is equal to 0. Now, we actually already know this because at t is equal to 0 is when we release the mass. And so what are we going to get? 3 centimeters. It's going to be at the amplitude at t is equal to 0, right? We pull the thing back and boom, there we go. I'm just checking something. Okay, good. Let me make sure I was using the right microphone. It would be horrible if this is all in horrible quality, right? But we can utilize y is equal to a cosine omega t. Now that we know a and omega, it's simply plug and chug, right? The cosine of 28.3 times 0, that's the cosine of 0. We get 1. 3 times 1 is 3. We call it a day, right? At 1 second, well, I'm just going to copy and paste this because it literally is a plug and chug. The only thing that's changing now is the time. So 1 second. Right, so the cosine of 28.3 times 1, so it's the cosine of 28.3. I'm going to throw in my calculator now. The cosine, this has to be in radians, the cosine of 28.3 gives us negative 0.999, right? So negative 0.999 times 3. Where is our thing going to be at 1 second? It's going to be at negative 2.999. If I wanted to do the rounding correctly, right? Centimeters. So at 1 second, where is our object? At 1 second, our object is on the other side of the equilibrium position, right? So if our mass started here, right, this is A, right? We stretched it out. I'm gonna make this longer. So we stretched it out. Here's the original equilibrium position. This is x is equal to 0. And here's the wall. At 1 second, our object is now all the way on this side, right? Almost to negative amplitude, almost to 3 centimeters. I guess I could make this even longer. There we go. Right, because it's obviously not going to go, it's not going to hit the wall. That's the point. Like the spring is supposed to be really long. Right, so where is our mass? Our mass is almost there. So it's not exactly here. Instead, our mass is somewhere here, right? Almost there, right? On the negative side, the opposite side, right? If this is the positive side, this is the negative side. Okay, but it is as simple as plugging it in. 1 second plugged into the time value, right? And the last one, 5 seconds. Once again, copy and paste it, because it is the exact same thing, but now it's 5 seconds. So 28.3 times 5 is 141.5. Now I'm going to do the cosine. The cosine of 141.5, and I get 0.991. Wait, did I do that other one right before? Let's just double check. Why are they so similar? 28.3 times 1. Yeah, okay. Yeah, they're just very similar. Whatever. They're just numbers that we ended up choosing. 28.3 times 5. You end up getting negative 0.991. It's like basically the same thing. Times 3. And so for this, it's going to be on the other side again, but now it's 2.97 centimeters, right? So it's a little bit that way, right? And this thing's oscillating back and forth, back and forth. I got scared because the fact that the numbers were so similar. I'm like, wait a minute, did I mess up on the other calculation? But no, I'm doing it right. I'm doing the calculation. That's funny. That's very good. Right. So that's what it is. Like, this is just what we do is simply plug and chug. If I want to know where the object is, I need to know the amplitude and the omega and at what time we're talking about, right? So 5 seconds, 3 seconds, 20 seconds, it doesn't matter. The point is that as long as we know what time we're looking for, we can then throw that into the equation. All right. Any questions about that? No? All right. The next problem. In this new experiment, the only thing that we change is the amplitude. Now, this is a typo. It says x is 80 centimeters instead of 40. It should be x is 80 instead of 3, right? Because 3 was the original, right? So that's obviously a typo. But the point is that the only thing that changed is the amplitude. What is the new period? Well, we said that the period is 2 pi over omega. The period of a spring specifically is 2 pi radical m over k. Amplitude is nowhere to be found here. Remember what we said about simple harmonic oscillators. Amplitude has no effect on the period. Therefore, T is, did I do that right? Yes, I actually, so there wasn't really anything that I had to change. I just had to answer those ones. Period is 0.71 pi seconds. The period did not change. All right. The period the amplitude has no effect on the period. You change the amplitude, it does nothing. In order to change the period of a spring, you need to change either the mass attached to it or the spring itself. You'd have to actually change the spring itself, like put in a brand new spring or put a brand new mass attached to it, or add mass or take away mass, depending on how the apparatus is. But the point is, the only way to change the period, 2 ways: changing mass, changing the spring constant, which means to change the spring itself. All right, amplitude, once again, has no effect on period. Yeah, we're okay? All right. Now let's talk about this last section. Like I said in that little video, these witnesses are not changing. You will be given the exact same sentences in this exact same order. Literally, this sheet you will be given. There's no change here. Each one of these things, each one of these statements, or each one of these witnesses is saying a truth of physics. I want to boil down what each one is saying right now, right? Because then the true false would come after. So witness A. And standing there in the company of springs, I did in fact witness a force that was proportional to the displacement of said springs from the equilibrium. Right here, this is our first lab. This is the relationship between the force of the spring and displacement. The force of the spring is proportional to the displacement. Fs is proportional to x. So if I now go over to here, and I'm going to look specifically, here it is, number 12, is where I see Fs and X. This is truth. Absolutely. This is a truth, right? Actually, I should use the same color, right? Let's be all consistent, right? This is absolutely a truth. Fs is proportional to X. Who said it? Witness A. Witness A said that Fs is proportional to X. It's what, their words say. And and this is true. Like, this is an actual true statement, right? We're okay so far? Right? This is basically a true-false matching. True-false in each statement is either true or false, and the matching is matching the true statement to the either true or false statement, depending on what it is. But what that means is that if you understand what these things are saying, if you actually understand and each one of these is like a motion or a part of a motion, if you understand this, then you already have the answers. Like, the answers are literally right here for you, right? It's not about just making sure that you understand what those answers actually are. So witness B, watching the rhythmic motion of the metal coil apparatus, also known as a spring, and noticing the changes, it was clear that varying the mass attached was having an effect on it, period. What is the relationship between the period of a spring and mass? The period of a spring is proportional to the square root of m. Part of motion 2, right? We determined the relationship between mass and period, and we noticed that it was a square root fit. So now, going over here, pendulum, spring. For a spring, T is proportional to the square root of M. Yes, that is true. Who said it? Witness B. Good so far? We're okay? You're following me? Stop me if we're not getting it. Hanging in. Good. C. There was something consistent about it, or was it constant? Anyway, there was something about the push delivered from the spring and its length it was pushed, but this was different from the stiffer spring. This is about K. This is about the spring constant, the stiffness coefficient. There was something about the push delivered, the force, and the length it was pushed. K is equal to Fs over X, right? That is the relationship of what a spring constant is. How much force you get per displacement. So coming over here, negative. Sorry, I forgot the negative, of course. My apologies. Hooke's law, negative kx. Sorry about that. Right? So going over here, and this is very suspicious that we're getting true, seeing that we have it here. K is equal to Fs over X. Number 8, K is equal to Fs over X. That is a truth. They're not all true. I don't think they're all true. No, they're definitely not all true. Right? Yeah, they're definitely not all true. I can see some false ones here. Right? Just have these 3 in a row happen to be true. And who said it? Who said that K is equal to negative Fs over X? That was witness C. Right, so it's all about knowing what the... Okay, good. Thank you for the confirmation, Jasmine and Quasi as well. Greatly appreciate it. As long as you guys are good, I'm happy to know. Like, if you're following along silently, I'm totally cool with that. Just want to make sure that I'm not losing anybody. All right. Witness D. Hypnotic is what it was, watching it sway back and forth. The angle at which it was released... Never even realized it varied. Guess it was of no consequence. So in this case, we're talking about a pendulum and how the angle at which it was released, also known as the amplitude, and I'll put in parentheses, angular amplitude, has no effect on the pendulum. So, period. And this is what I want to write, but there's no symbol for this, unfortunately. Period is not proportional to theta. Period is not proportional to angular amplitude, right? Angular amplitude there. How it's going to be written, though, so Just a heads up. I'm going to say not equal to. Same thing, I guess, but I really want non-proportional, but like you can't find that symbol, which annoys me, like in Word. So we have to stick with not equal to. So what I'm looking for is T, the relationship between period and angular amplitude. So let's take a look here. Oh, this is another true one. What the hell? Obviously the trues don't fall in line, but it turns out like the first 3 or 4 are going to be true, or 4 or 5, I should say. For a pendulum, T is not equal to theta. That is absolutely true. And who says it? Witness D, right? A, B, C. Yeah, A, B, C, D. It's very funny. I never realized. I don't think I did it this way. I think I did it the other way, and I never noticed that it happened this way. But yes, this is absolutely true. It is true that period is not proportional and has no equivalence to angular amplitude, right? That's what that is, angular amplitude. And so that absolutely is truth. And we saw that in motion 3 when we varied mass, angular amplitude, and string length. We saw that only one of those things actually changed the period. But I digress. We're going to see that in just a moment. Witness E. Mass? Mass? Do they not even know Newton's second law? How could that which oscillates due to gravity's varying pull in the direction of motion be influenced by such a thing? So once again, oscillates due to gravity, that's a pendulum. Mass has no effect, right? How could it be influenced by such a thing? Mass has no effect on the pendulum of the period of a pendulum. And I should be doing pendulum like that. Period of a pendulum, period of a pendulum. Mass is not in any way proportional to the period of a pendulum. You change mass, it does nothing to the period of a pendulum. And the reason for that is because as we saw in Physics 101, mass does not affect acceleration due to gravity. mg is equal to ma, right? When we say mg is equal to ma, oh, look, mass cancels out. Acceleration is always g, no matter what the mass is, right? Rahel, absolutely. Rahel asks in the chat, length does have an effect, right? And that's absolutely. We totally are. Oh, wait, is it not? I didn't miss. Oh, do I not have it on here? Huh. I don't have that on there, but absolutely, length totally does. Wow, really? I can't believe I skipped that. Maybe in the future I'll add that one. But yes, length absolutely does. Length of the pendulum absolutely does, and specifically, I'll write it here on the side, right, in a different color, so it's not part of the original notes. The period of a pendulum is proportional to the square root L, right? That is absolutely true. This is from Lab 3, Motion 3. We saw that. But I can't believe I don't have the string length. That's weird. Okay, I could have sworn it was on here. But all right, that's fine. I thought we were going to get to it. But no. So the period of a pendulum has no proportionality to mass. So let's take a look here. Pendulum. Aha. T is proportional to square root of m for a pendulum? No way. Jose, that is false. Who told us it's false? Which witness told us the correct statement? Which witness told us that mass has no effect? Oh, that was witness ABCD E. Yes. Right, witness E told us that it was false, right? So the witness will always tell you truths, right? These guys here, they're always factual. What might be false is these statements here, right? And the point is that like if this is a court, what we're doing is comparing what the claim of like the defendant is, right? The defendant claims this thing, but no, I have a witness that says otherwise. I have a witness who was there and observed it and knows otherwise, and so the witness's testimony is what's being used to make these true or false. Something about a court motif. I don't know. Infinity court. Who knows? F. Simple. It was harmonic. Simple harmonic motion. No doubt. Too smooth not to be. Like a smirkle. 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 Why did that get me so? Like a circle. Smooth, but up and down. Why is Smirkle so funny? That really, really got me. A perfect. Yes, a perfect Smirkle. Simple harmonic motion is smooth cyclical motion like a circle, but up and down. What is witness F talking about? Witness F is talking about a spring. A spring is smooth, cyclical motion that is simple harmonic, right? Smirkle, absolutely. Yeah, I think it's something about right. It's Smeagol, it's Smurfs. Something's getting me. I don't know what it is. I'll talk to my psychologist about it. Right, a spring is simple harmonic motion that is smooth and cyclical, like a circle, but not circular. Right, nothing's moving in circles. Instead, it's up-down motion. And so when we say something like "there is no way to describe the motion of a spring," I call BS on that because witness F tells us that it's smooth, cyclical, simple harmonic motion. There is a definitive way to describe the motion of a spring, and that is that it's simple harmonic motion, right? It isn't random motion. It has characteristics. It's its own model of motion, which we can quantify. Whew. Process circle. Excellent. Good. Well, see, right, this right, this silence, right? This total silence. And I worry that like I'm losing people, but it's good to know that like no, you guys are still there. Good, 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 fantastic. And I know that you guys are good. I don't have to worry about you guys fading off because in general, you guys are on top of the ball. You guys are just actively listening, which is good. All right. So there's no way to describe the motion of a spring. No, the motion of a spring is simple, harmonic, smooth, and cyclical. That is what the motion of a spring is. Now, for the example, the little example that I gave, I already went over witness G, right? Alpha and omega. So we're talking about omega. Omega is required to determine period, which means that omega must be radians per second. And that is what the definition of omega is, or the units of omega is, I should say, right? No, cool cat. No, you're cool cat. No, they didn't mean it that way. It is all good individual who is named cat. Yes. So like I said, omega 1, that's done. Go look at that little thing if you want to see the full explanation. But witness H, I really should have paid attention. Cos, yes, it's written that way for a reason. I know that I've seen this function before. Whatever it might have been, at least I know it was a function that describes all harmonic motion. This is y is equal to a cosine omega t, a cosine function that we've seen before, right? It is something that describes all simple harmonic oscillators. And so, excellent. Sorry, Kat. Sorry about that. So, y is equal to a omega plus t squared describes simple harmonic motion. A false. We know that witness A, B, C, D, E, F, G, witness H says otherwise. Witness H says, oh yeah, thank you, Skylar. Just about to say it. Witness H says to us that a simple harmonic motion or simple harmonic motion is a cosine function. And sorry, guys, I might go over a little bit. If I do, I'm sorry. You have permission to leave if you have to leave. If you want to stay, please stay. But of course, this is a recording, so it's going to be posted. So don't worry about that. Oh, and before you do leave, right? Before you do leave, Lab 5 is not going to be due next week because of the whole thing with the midterm and the midterm review and all that. We decided to take waves out of it, right? Because you guys went over waves in class, but we weren't sure whether or not we wanted to do waves. It's now solidified that waves, I'm not mistaken, and I will confirm this, of course, once again, waves should not be on this exam now that like the review is out. Right, no, that's good. Rahel, it does not mean that we're not doing waves at all. It will just be on the final. So that means it's like a boon for the final, right? Like that's a helpful thing in some ways, not waves. So yeah, I'm gonna change the due date to Lab 5. I'm gonna work with something and see what I do. Like yeah, like there's no point of having you do a lab on waves if the exam isn't on waves. Like that won't be helpful to you. It's just like making you do extra work for something that isn't like what you should be focusing on. So yeah, it's not going to be due next week. I changed my mind on that. So no fight for me, right? Exactly. Yeah, good, excellent. So that's fine. Right, I know. Everybody here is clutching their pearls, so upset of the news. But like I said, if you guys have to leave, I know that now it's officially done. Please go. It's going to be recorded, so don't worry. But I'm also here. Like I'm going to still keep on trucking on. I'm not stopping until we're done with this thing. So as I said, y is equal to a omega. Omega plus t squared, false. That is not simple harmonic motion. Witness H says so. Yes. Peace be with you, Skyla. No problem. Right. However, I did say there was no waves, but we went over it in lab, so this is on here, right? So this is the only thing on. Oh wait, no, I'm actually gonna take it. I'm actually going to pull one out. Witness J is out. All right, I'm not going to give you witness J for this exam. Okay, which means one of these things is going to go away. I'll answer it for you. No problem, Quasi. That's fine. Like I said, there's a recording of this, and so if like you are okay for right now and you have no questions, don't don't feel bad to depart. You're totally cool. No, I totally get it. And right, this is why I'm recording it, so it's no big deal. So yeah, peace to all who's got. If I end up just being by myself, I guess that's totally fine too. Like that's no issue. But right, as I was saying, I'm gonna get rid of witness J entirely, so don't worry about witness J because that's something we actually didn't talk about in lab. Somehow I skipped that part of lab 5, so that's fine. Yes, peace to all who are leaving. But witness I am totally leaving in there. This has to be sci-fi. Oscillating within both space and time, you will make waves with that claim. This is specifically for Rahel. A thing that oscillates in both space and time, something that is simple harmonic motion in both space and time. What is that? That's a wave. And so, going over here, y is equal to a cosine omega t, time, and y is equal to a cosine kx, space, describes wave motion? Yes, that is true. And who says that? A, B, C, D, E, F, G, H, I, witness I, says so. I'll just flat out say it here. The velocity of a wave in a given medium can change. This is false, and that's witness J. I told you we're skipping it, so I'm going to cut it. I'm going to cut it from the document for the exam. So don't worry about that. Peace to all who have left already. My apologies for going over. But like I said, we're going to go over the whole thing. The next one here, witness K. I don't believe you understand the gravity of this situation. The time for an oscillation was inversely related, and I believe even raised to a half power. This is specifically talking about a thing that oscillates due to gravity. This has to do with the period of a pendulum and how it's proportional to the square root of 1 over g. Inversely proportional, 1 over g. Raised to a half power, the square root. So for the period of a pendulum is proportional to the square root of 1 over g. Looking here, the period for a pendulum is proportional to the square root of 1 over g. That is absolutely true. And who says that? Hij, k. That's k. And already we know Hij, k, l. Right? This is witness L. It's the last one. That's what's nice about the matching section is that you could always just fill in the last one. But let's actually look at it, right? One cycle is pi over 2. Cherry, blackberry, it doesn't matter. 2 pi's is enough to get you there and back. 2 pi is 1 cycle, right? This is what we were talked about just before in that previous section, right? 2 pi is 1 cycle. Therefore, when I look here and it says 1 full cycle is pi over 2, no, that is false. We were told by witness L that 2 pi is 1 full cycle. Woo! Now that's what I call a review, ladies and gentlemen. Are there any questions? I know that a lot of you have left, and by all means, that's no problem. But if there's anybody here who has any questions, please do not hesitate to ask. And I also say, those of you who've gone already, and if you're listening to the recording, don't hesitate to shoot me an email if you have any questions as well. Remember that when it comes to an exam, the worst thing that, absolutely, Kat, good question. Happy to see you're still here. The worst answer that you could ever get when asking a question about an exam is, I can't answer that, right? Like, ask any question you feel that you have, because if I can't answer it, then I just can't answer it, right? And I'll tell you that. But if you're confused about anything, if you're confused about formatting, if you're confused about wording, if you're confused about what a question is asking or anything like that, by all means, ask it. And I'm also saying this, and I'm totally saying this, maybe I'll say this off the record. I'm totally going to say this off the record because, I'm totally going to say it off the record. Are there any other questions? I'll say something off the record. I'll take my answer off air. Any other questions? No? Okay.